Okay, sweet. So hi everybody. Welcome to the first review for Bio285. I'm Sebastian. I'll be one of your TAs. Rachel is our other TA for the course. Unfortunately, she had a lot of work today, so she won't be able to make it, but she'll definitely be here in the review on Friday. So before I start, I just want to get out any logistical questions out of the way. Do you have any questions about maybe how the class works, like how check-ins work? What are check-ins? What are your responsibilities for the discussion forum? Anything to that effect?
Check-ins.
Yeah.
So for this review session, can I check in for the session?
Yeah, so usually reviews don't count as check-ins only because during the regular semester, there was obviously a lot of students in the regular semester. There was almost 200. So we would get a bunch of people going to the review sessions. So it was very hard to keep track of everybody at the review. And during reviews, you also don't really get that kind of personal interaction that you do as if you were to email your TA or the professor or go to their help sessions. The point of a check-in is essentially for us to make sure that you haven't fallen off the face of the earth or something, or that you're up to date with the material, that you're okay with the material. So it's mainly just what it sounds like. It's to check in. And during the regular semester, reviews didn't really count as check-ins only because there were so many people and you don't really get to have that interaction with students. But because this is a relatively small class, I think there's only 17 students or something. I could probably make this one count as a check-in. Pretty much if I get the sense that you're okay and that you're not struggling with the material, or all of your questions have been satisfied, I could see how that counts as a check-in. So I could do that for this week. So that's pretty much the purpose of check-ins. I believe it's one check-in per week, and you could either email me, Rachel. Our email addresses are here, or you could email the professor, Dr. Francis. Go to our help sessions, which are office hours essentially. Any one of those things count as check-ins. So that's the point of those.
Got it. Thanks.
Yeah, no problem. Okay, so I'm gonna go through this. If at any point you have a question, you could just drop it in the chat. I'll try to be paying attention to that. And if at any point you have a question about anything, of course, feel free to interrupt me. That's totally fine. And I'll clear up any points of confusion. All of these reviews are recorded. They're going to be uploaded into this YouTube page that we have. At the end of the session, I'm going to send another email class reminder. I'm going to send the link to this PowerPoint as well as the link to the YouTube video. And I'll just give a little intro about what the YouTube channel is. It has all the reviews from the previous semester. So in case you want extra support, or you want an extra video to watch to help your understanding, you have all the ones from previous semester accessible to you. So again, I'll write all that in an email, so it's more understandable. But anyway, okay, so amino acids. An amino acid is essentially this compound right here. It's also called a peptide. All peptides are composed of the same groups. So all amino acids, they're called amino acids. As you can imagine, there's an amino group, there's a carboxylic acid group, hence the amino acid, and they all have the exact same structure, except for this R group. They all have a backbone, which the backbone is the amine group, this hydrogen, the carbon, and the carboxyl group. It's essentially everything that is not the R group. The R group is the side chain. I'll talk a little bit more about what the side chains are. But as far as a basic amino acid structure, this is essentially all its structure. Laura usually likes questions that ask you to differentiate between the backbone and the side chain. So just try to keep that in mind. And I'll be referencing the backbone and side chain pretty often too. So again, the backbone is just all of this. The side chain is just your R group. And I'll talk about what an R group is later on. So I have some questions here, but I feel like I could answer these questions with an example in the next slide. Okay, so as you probably saw in this week's lecture videos, peptides never really exist like this. Peptides don't just exist as one molecule. more often than not, or almost always, peptides are going to come together and they're going to form a chain, kind of like this. This is also called a polypeptide chain, hence poly, like multiple peptides forming this chain. And this polypeptide chain is called the primary structure. So all proteins or all, proteins are essentially a bunch of peptides that have come together that are folded in a different way. But before we get to talking about like proteins in the traditional sense, the primary structure is just when one peptide, when one amino acid comes together with another one, like this one, and it starts forming this chain. So a byproduct of this chain forming is it releases water. These bonds holding the peptides together, that's called a peptide bond, pretty easy to remember. And this is a kind of covalent bond. Covalent bonds are, are like specifically, they're, how do I say this? They're regarded as like pretty strong bonds, which makes sense that your polypeptide bond would be a strong bond. You obviously don't want your protein chain to be falling apart. You don't want this chain to be disassembling. So it makes sense that the bond that holds peptides together is a relatively strong bond. That's called the covalent bond, as opposed to other bonds, which I'll be talking about in a minute. So any questions about the primary structure so far?
No, thank you.
Yeah, no worries. Okay, the secondary structure is, I forgot to mention. Primary structure is, again, it's held together by peptide bonds. It's a type of covalent bond, but the only interactions happening is within the backbone. So the side chain, the R group, it's not relevant yet. So far, we're still only talking about bonds that exist in the backbone. Secondary structure is, so after you have your polypeptide chain like this, this is where the backbone is going to start forming interactions with each other. So after the primary structure, secondary structure is when your polypeptide chain starts folding into like these funky shapes. Like this is an alpha helix. These are beta sheets. And again, these are bonds between the backbone. There's still no bonds between the R groups yet. These bonds that make secondary structures, these are hydrogen bonds, which they're definitely nowhere near as strong as covalent bonds. These are a kind of electrostatic bond. So far we've talked about a covalent bond called a peptide bond and an electrostatic bond called a hydrogen bond. They're much weaker than covalent bonds, so they are more susceptible to breaking. Obviously, you don't always want that, but they can, I guess. Hydrogen bonds are not covalent bonds, like I just said. And again, secondary structure only involves the backbone. It is not it only involves the backbone. It doesn't involve the R group yet. Okay, any questions about any of this?
No, it's fine. Thank you.
Yeah. Okay, so that was primary and secondary structure. To talk about tertiary and quaternary, we need to talk about what these R groups actually are. So here's your amino acid chart. You're probably going to be referencing this a lot, especially during like quizzes or exams or something. But notice that these are all of your amino acids. And everything that you see here, what classifies an amino acid as a particular amino acid? Like what classifies a proline as opposed to a cysteine, as opposed to a valine, is the different R groups. So again, all amino acids have the same backbone. Here's your amine group, here's your carboxylic acid group. All of these have the same group. What makes them different is their R group. So you have nonpolar R groups, you have polar R groups, charged polar, positively charged polar, negatively charged polar. Polar molecules are hydrophilic, meaning that they bond well with water. Nonpolar, so all of these guys, these are hydrophobic R groups, whereas all of these are relatively polar R groups. So the hydrophobic effect, which is essentially like how the protein is going to be folding into its tertiary structure, which again, I'll talk about in a little bit. The way the proteins fold is they conceal their non-polar R groups inside. So when you're folding this secondary structure, so again, you have your polypeptide chain. This polypeptide chain forms hydrogen bonds to make these like funky shapes. And then these shapes are also going to be folding into each other. But the orientation that secondary structure is going to be folding into each other depends on the R groups. The non-polar hydrophobic R groups are going to be tucked inside, whereas the hydrophilic polar R groups, are going to be tucked outside. They're going to be sticking out of the protein. Okay, so a popular question that you'll see in this class is something like this. So if you have a peptide chain of 10 amino acids, what will happen to the protein in terms of folding if the fifth, so like the polypeptide in the middle, what if you change it from a valine to a glutamine? So let's find valine. Valine is here. It's a non-polar amino acid. What if you change this valine into, what did I say? A glutamine. Where's glutamine? Oh, okay. So notice what you're doing. You're changing a non-polar amino acid into a polar amino acid. So what does this mean as far as folding? It means that now, because you've changed a non-polar R group into a polar R group, this polar R group is going to try to resurface. So whereas this amino acid was tucked away inside the protein because it's non-polar, now because you've changed it to a polar amino acid, it's going to try to flip outside, or it's going to try to fold in a position where this R group that you've changed is now sticking onto the outside. And again, questions like these are very popular in this class. Like you might see them, what if you go from a glutamine to a cysteine? Where's cysteine? I can't find it. Oh, okay, I found it. Okay, so again, you're going from a polar amino acid to a non-polar amino acid, which means instead of this R group trying to try to stick outside into the environment, it's going to try to tuck itself inside in a hydrophobic environment. So does that all make sense so far?
Yep, but I have questions. If you change from a nonpolar R group to another nonpolar R group, will that have any differences?
That's a good question. That actually is a good question, and it depends on the amino acid. So as far as like the chemistry of it, no, because if you're going from nonpolar to nonpolar, maybe the folding won't be affected too much. But let's say, for instance, you're going from an alanine to something like this, like tryptophan. Do you think that there would be, or like what differences would you expect if you go from an amino acid like this to an amino acid like this? Can you think of any like off the top of your head?
Like, is it more hydrophilic, stuff like that? I don't know.
It's so notice the size in this R group. This is a very small, it's just like a little methyl group, whereas this R group, it's a huge, bulky, you have a phenyl group, you have like two different cyclic groups here. So that's a good question because in addition to thinking about whether you're going from polar to nonpolar or positive charge to negative charge, you also have to consider the size. Notice if you're going from something like cysteine, which is relatively small compared to an amino acid like phenyl. I'll say this one because I can pronounce it. If you're going from like cysteine to like tryptophan, obviously there's a huge bulky size here, which it actually may affect the folding of the protein because you're going from something relatively small to something relatively big. Even though the chemistry hasn't really changed, even though they're both technically nonpolar, because you're changing a relatively small amino acid into a relatively big one, into a relatively bulky one, yeah, it may actually have an effect on how these guys interact. Oh my God, stop. So does that answer your question?
Yeah, thank you very much.
Yeah, no problem. Okay, so tertiary and quaternary structure. Again, in primary and secondary, oh my God, in primary and secondary, we only talked about interactions with the backbone. However, tertiary and quaternary, now these guys do involve interactions with the R group, with the side chain. So a tertiary structure is just when, so again, here you have your primary structure, it's just the polypeptide chain. You get secondary structure when the backbone starts making these hydrogen bonds forming into these like silly shapes. And then when these shapes fold onto themselves and start forming this like big, not this big thing, but like this bulky, weird thing, that's a tertiary structure. So it's when everything just starts folding onto each other. A quaternary structure is just when multiple of these proteins come together. So here you see like a chain that's like a light blue, and then you have another chain that's a dark blue. These are two tertiary structures that have bonded together. Because they're bonding together, this is why it would be considered a quaternary structure. So that's all quaternary structures are so far. Okay. And again, if you have any questions, like feel free to interrupt me. Okay, so the chemistry behind tertiary and quaternary, again, now the R groups are becoming relevant. In a polar charged R group, these form ionic bonds. Okay, so best way I could do this is polar uncharged. Yeah, okay. I'll have to go back to the diagram, but when you have an R group connect, this is another kind of like popular style question. So a question might be like, what kind of interaction would you expect with a lysine and aspartic acid? So you'd have to go back to your chart. So if you have two polar uncharged, these are polar charged. This is polar uncharged, and this is nonpolar. So if you have two polar uncharged groups coming together, like the serine and the tyrosine, for instance, the bond that would form here is a hydrogen, a hydrogen bond. But if you're making a bond between a lysine and aspartic acid, notice that you have a positive charge and a negative charge. Because you're dealing with charged amino acids, now you're forming an ionic bond. If you have a nonpolar group coming together with another nonpolar group, the only interaction that you're going to get is a hydrophobic interaction called a van der Waal interaction. I know this is like a lot to take in right now. I have a little chart with like all the different summaries, or like a bond summary with everything that I've talked about so far. But essentially, when you have, this is also another good slide with like the different interactions. When you have polar charged R groups, so anything in these columns, when you have any amino acids in these columns coming together, you're going to form an ionic bond. When you have any two polar uncharged R groups, so any amino acids in this column, when any of these two amino acids come together, you'll get a hydrogen bond. And when any nonpolar R groups, so any amino acids in this category, when any of these two R groups come together, you'll get a van der Waal interaction. Okay, so notice here you have two, I think these are two valine. Notice that these two valines are coming together, which is why you have a hydrophobic interaction, also called the van der Waal interaction. Here you have two polar amino acids coming together, which is why they have a hydrogen bond. Here you have two polar charged, opposite charged, by the way, because a positive charge can't come together with another positive charge because alike charges repel each other. So here you have an ionic bond because you have a polar positive charge coming together with a polar negative charge. I'll talk about disulfide bridges in a second. But before I get to that, do you have any questions so far about anything here?
No.
Okay, sweet. Okay, disulfide bonds. These are special kinds of bonds that only exist between two cysteine molecules. So anytime you have two cysteine, when you have two of these guys coming together, you'll form something called a disulfide bond. Disulfide bond is a kind of covalent bond, which means that it's a pretty strong bond, as opposed to van der Waal interactions, which are very, very weak, and hydrogen bonds, which are electrostatic interactions, which also are not as strong as covalent bonds. These are two very kinds of, the disulfide bonds or disulfide bridges are very strong kinds of covalent bonds. Okay, so suppose you needed like a molecule that needed to like bend around, like the purpose of the molecule is that it needed to like flex around, it needed to bend and whatever. Could you imagine that molecule having a lot or very few disulfide bonds? What do you think?
A lot.
It would actually not need that many. If the purpose of the protein is to like bend around and be very flexible and be very like malleable, like be able to move it around a lot, these are very strong disulfide bonds are very strong kinds of bonds, meaning that they're like solidifying the structure a lot. It's kind of like how can I put this? It's like, you know, clay. Like clay is obviously very like malleable. You could shape it into whatever you want very easily with your hands. But after you cook clay, it becomes very solid. You can't bend it anymore. That's essentially what the disulfide bonds are doing. They're like solidifying that protein. They're making it very sturdy. They're making it very stiff, very stable. So if you wanted a protein that could move around, that could bend a lot, that could flex a lot, and just be very malleable, you wouldn't really expect to find a lot of disulfide bonds in there because again, disulfide bonds are very strong kinds of bonds. They're covalent bonds that really solidify the structure of that protein. So say you had a protein like an antibody that was supposed to travel around the bloodstream. So the bloodstream, our bloodstream, it's usually a very harsh environment. There's uh, there's like high acidity going around or low acidity. Um, well, there's like a lot of like pH imbalances throughout the bloodstream. It's usually a very harsh environment for proteins. So antibodies obviously do travel through our bloodstream. Antibodies do require a lot of disulfide bonds because you need them to be very stable. Because of the fact that the bloodstream is such a harsh environment, you need a protein that's capable of being very sturdy, that's being very solidified or strong. Does that make sense?
Yeah.
Sweet. Okay, so here's that bond summary that I was talking about. Covalent bonds, these are very, very strong kinds of bonds. Non-covalent, these are like your weaker kinds of bonds. So the two covalent bonds that we've talked about is peptide bonds, which hold amino acids together. Disulfide bonds, which is just like the cysteine interactions. Non-covalent bonds, ionic bonds. So when polar charged amino acids come together, hydrogen bonds, when polar uncharged amino acids come together, van der Waal, two non-polar amino acids coming together. So in a protein's primary structure, again, only the backbone is involved. You're really only dealing with peptide bonds. Secondary structure, still only the backbone is involved, except in secondary structure, you're not working with peptide bonds. You're not working with covalent bonds. You're only working with hydrogen bonds. In tertiary and quaternary structure, both the backbone is going to be involved, and especially the R groups are going to be involved. And these will have a combination of both covalent and non-covalent bonds. Okay, domains and subunits. So a domain is just, so obviously you probably know a protein is responsible for some kind of function. Like maybe you need a protein to like cleave this bond, or you need it to do something. A domain is a part of a protein that it folds independently, but like, what does that mean? A domain is just a part of the protein that does something. So again, let's say you need a protein responsible for breaking, let's say you needed a protein that's responsible for breaking a peptide bond, like an enzyme, for instance. That protein or that enzyme would have a domain, which the domain's purpose is to cleave this bond. Maybe that protein has a different domain, which purpose is to form a bond. So a domain in a protein is just a part of a protein that carries out some kind of function. One protein could have several domains. Yeah, so just bear that in mind. It's not one protein has one domain. Like you could have one protein that has like a bunch of different domains. Each of those domains doing different things. Okay, subunits are only talked about when we have quaternary structures. So quaternary structure, like I mentioned before, is just when two or more tertiary proteins come together to form like this really big shape. Notice the light blue is one protein, the dark blue is another tertiary protein. When they come together, they form quaternary structure. So quaternary structure is, again here, the red is one tertiary structure, the blue is a different tertiary structure. Each tertiary structure in a quaternary protein is called a subunit. So this protein looks like it has two subunits. I'm only basing that because I see one red and one blue. So it looks like it has two subunits, but like, I'm not sure how many subunits this actually has. Okay, any questions about this?
Like I have a question
Yeah.
for the short answer response. Like
Yeah.
it is asking whether a hemoglobin has domain or not. And I'm kind of confused because I think it has like two domains, but I'm not sure.
For which long answer was this?
I think it's the third question for the short answer response that we have to submit tomorrow
Oh,
and turn it in.
okay. Honestly, haven't looked that out yet, so I can check out that question just to be like absolutely sure. Just to be absolutely sure, I could check that out and then I could email you um, maybe a more detailed answer, because right now, like off the top of my head, I don't really remember exactly what the domains of hemoglobin were. I know that hemoglobin
Okay.
is a quaternary structure composed of like 4 different subunits, but I don't remember
Yeah.
specifically if it had some kind of domain function.
Okay.
Yeah, I'll definitely email you sometime later tonight though.
Okay. Thank you very much.
Yeah, no worries. Okay, protein structure models. So these are just the different kinds of models that you can illustrate proteins. There's the ball and stick, space filling, backbone, um, things to that effect. So each of these have their like pros and cons. Here's a list that like kind of gives you a better explanation of what each of these do, as well as some pros and cons. You might see like maybe like one question about this on like an exam or something, or a quiz. So I'm not gonna go through all of this because I know I know you guys can read. So I'm not gonna go through like every single one of these, but just bear in mind that some models are better for other things than others. So for instance, if you wanted to know like the overall shape or like the size of a protein, like how much volume it would occupy, maybe your backbone model isn't going to be the best for that. Uh, if you were looking for how much space or how much volume your protein occupies, it seems like the space filling would be a better model for this because it shows you like the actual van der Waal radius for each atom. So that would be this would be a better model to use for that particular case. Okay, what else do I have? Okay, so just a couple true or false questions, and then we're all set, and I'll look into that hemoglobin question for you. So what do you think? If a protein unfolds, do you think its solubility will change in water?
I don't think so.
Yeah, so water's like, as you probably know, water is a polar it's a polar molecule, meaning that like a cup of water. So if you have like proteins in a cup of water, um obviously the environment is polar. If polar mixes with other polar things. And like I mentioned before, proteins when they're folding, they want to tuck away the hydrophobic R groups. So anything that is nonpolar, they tuck away on the inside. And the only R groups that they expose are the polar R groups. So because your polar R groups are on the outside and they're combining with the polar environment, with the polar water, they do mix very well. Like they are very soluble with each other. However, if a protein unfolds, like maybe you change the environment or whatever, like you messed it up or something, if that protein unfolds, you're now exposing the hydrophobic interior. And because you're exposing those hydrophobic R groups, you actually are changing the solubility because now it's not mixing very well. Now, as opposed to having your polar R groups sticking out, now you have your non-polar R groups sticking out of the protein, which messes up with the solubility of water. Does that make sense?
Yeah.
Yeah. And this one, I kind of answered it early. So a protein with one polypeptide can have multiple domains. That's definitely true. You could have one primary structure that folds into different secondary structures that folds into a tertiary structure. That tertiary structure can have a bunch of different domains, not just one. Okay, so that's all I have now. Do you have any questions before I log off, I guess?
No, no. Thank you very much.
Yeah, no problem. And I'll definitely email you with whatever I figure out about that question.
Thanks.
Yeah,
Hi, Sebastian.
who's here? Oh,
Rachel, I literally just got home from work.
no, you're totally fine. Well, I just finished, so but
Okay. How'd it go?
Yep. All right.
Did it go okay?
Yeah, I mean,
Okay.
we're just vibing right now. Does anybody have any other questions before we split? Oh, actually, Rachel, now that you're here, okay. Sorry for whoever asked early. Do you mind repeating what your question was about the hemoglobin? I remember we talked about it last semester, but I honestly don't really remember the specifics behind that question. Do you mind just like repeating that one more time, please?
Yeah, like I don't know how many domains are in hemoglobin, and I'm not sure.
Okay, wait. So just about hemoglobin, like, was it about like domain versus subunit, something like that?
Yeah,
Okay.
there's like a question on turn. Like we have to submit tomorrow on Turnitin.
Yeah, the
Mhm.
problem set.
Yeah.
Okay. Wait, it's on the problem set?
Yeah.
Which question?
Like
I
th-
Did you send us the problem set?
So
Sebastian?
no, she hasn't.
Oh, good. Okay.
Yeah, it's all right. I know, like off the top of my head, I know that hemoglobin has 4 different subunits. I know each subunit has a heme protein, which is like what attracts oxygen onto it. So that obviously, hemoglobin, its purpose is to like carry oxygen around throughout the body. So it has this protein that that attracts oxygen. It's not a protein. I think it's just like an iron molecule. I think it's just metal that attracts
Yeah.
oxygen, and that's how it carries it around. I don't remember if it has like any specific functions. You know, maybe
The
the heme.
subunit itself or the iron?
Yeah, like I don't know if the iron is like counts as a domain because it does like
I don't think it does, to be honest. I don't,
Yeah.
because iron's not a protein.
I'll have to double check and ask Laura for
Yeah.
that because that'll be clutch.
Yeah.
Okay.
Yeah, I wouldn't say it counts as a domain, but I'm not entirely sure about that.
Yeah, same. So, okay, I'll try to figure it out tonight. For whoever asked, and I could send you I could give you a better explanation over email.
okay.
Yeah.
So do I have to give you my email or?
I think we have them all.
Yeah. I know
Okay.
that's strange,
Okay.
but I think we have them.
Okay.
Also, Sebastian, is there something that says that we're doing them at 6:30? Because more people joined around 6:30.
Did
You said 6, but I wonder if Laura said
oh
6:30.
um
Undergrad.
did I say 6:30?
No, you.
I know my reminder said 6. I don't know if Laura
Yeah.
said 6:30. For anyone here, did you guys see 6:30 by any chance?
Yeah, I got an email from her that said it was going to be.
Oh
at
yeah,
6:30.
it says on Moodle 6:30.
Damn.
Wednesdays and Fridays 6:30.
Yeah, that was my bad. I don't know why I thought 6. Damn. Okay, that was my bad. If it's any consolation, all of this was recorded. I'm gonna post it. I'm gonna upload this onto our YouTube page soon.
Yeah.
I could take any since this was like definitely my bad. I could take any questions you guys might have now about like anything here. Let me actually. Oh no, I don't think I can yet. So, do you guys have any questions about anything? I'm sorry, I feel so bad now.
At least it's recorded. You're chilling.
Yeah.
I just have a question about the quizzes. Are they open notes? Or are we supposed to be doing them without notes? Like, what's the protocol?
I think they're open note.
Yeah, there's no like real way to
Yeah.
like enforce that. So I'm pretty sure they're open note. What is not, or sorry, I think like all resources are available to you, except when it comes to exams. I think for exams it's open book, but you can't consult with your friends. That's the only thing.
Yeah, that's about it, I think, for the quizzes.
And then for like the check-ins, do we need to like I attended this and this will count? Do you guys just have that recorded that I'm here? Or do I need to also email her?
Are we counting the review sessions this time, Sebastian?
So I was saying that during the regular semester, like during this past semester, we didn't count review sessions as check-ins, only because there was like a substantial amount of more people at
Right.
review sessions, and it was like check-ins are essentially us to make sure that you guys are okay, like you're not struggling with anything, and that
Yeah.
you're fine. And you can't really get that in a review session because like it's less like interactive.
We'd
It's
have like 30 people like last semester.
Right. So review sessions normally didn't count as check-ins, but because this class is only like
15
because it's only
people.
like yeah, it's like
Yeah.
15, 17 people. maybe I would have to ask Laura.
I think it'd be fine. I mean, we can ask Laura, but like, I honestly like, this is about the amount of people I'd get during my help sessions anyways, and those.
Yeah.
So, you know,
Yeah.
I feel like it's fine. But yeah, to answer your question, after every Zoom meeting, we can see like who logged in. And then we just take down the names.
Yeah.
Perfect. Thank you.
No
No
problem.
problem.
Nice. Okay. Yeah, I'm so sorry about this. I even told Laura, like I emailed Laura, I was like, okay, we decided 6:30 was good. And then something possessed me and I was like, oh, it's definitely at 6, not 6:30.
Oh God, that's funny. At least it's recorded.
Yeah, that's true. That's true. I promise we'll do better next time.
This stuff is also, I mean, compared to other things in this class, this is one of the easier topics. So hopefully people won't have too many questions on it. But even if you do, you obviously can always email either myself or Sebastian.
Right.
Definitely. Awesome.
Okay, so
Awesome.
before I split, do you guys have any other questions about anything?
I'm all set. Thank you, though.
Awesome.
Okay. All right. Have a good one, everyone.
Bye, everybody.